Hello. Hope you did a good job on your quiz. So this is your homework to watch this video. 5.1 is on limits and convergence. So we're actually going to begin calculus now. All right, so the objective, students will be able to compute limits of a function and determine the convergence. So we actually did convergence in our sequences unit already. So we're going to start with a definition. It says, if f of x approaches a real number L as x gets closer to, but not equal to, a real value a, for both x less than a and x greater than a. Hey, that's coming from the left-hand side and the right-hand side. Then we say that the limit of f of x as x approaches L. We write this as the limit as x approaches a of f of x equals L. I have a little QR code if you're interested in something interesting. All right, so the first method for limits is to find limits numerically. And that's actually what we did in chapter 4 with our rational functions. One of our methods was to do it numerically. Numerically means you set up a table and you choose values from the left-hand side of that x value and values from the right-hand side. So it says find the limit numerically of f of x equals x squared minus 1 over x minus 1. In other words, find the limit as x approaches 1 of x squared minus 1 over x minus 1. Go ahead and pause the video and fill in the table. All right, so what I've done is here's my values. Now if I plug in 1, that's undefined, so just go ahead and say that. Okay, so here's the interesting part, and we're going to actually write this above it, okay? So watch this. I need to look at what's happening as I come in from the left, and it's okay to write f of x, or you can write out the function. Either way is okay. So as I come in from the left-hand side of 1, so that's coming on this way, what number does it appear to be approaching? To me, it looks like 2. Then I look at the limit as x approaches 1 from the right. So that's 1.4, 1.3, 1.2, 1.1. It's going to 2. So then the limit of x going to 1 of x squared minus 1 over x minus 1 is in fact 2. So here's a key concept. Here's the key concept. In order for a limit to exist, the right-hand and left-hand limit must approach the same value. So what's going to happen is you're going to always have to find, let me change colors because this is fun, the limit as x approaches a from the right of f of x, if it equals some number L, and then the limit as x approaches a from the left-hand side of f of x is this same number, then we conclude that the limit exists. So this is the method to do it numerically. Another way to do it is graphically, okay? And we actually did look at this in chapter 4 as well. So this should be like, just let's tackle it one more time. So it says, sketch the graph of f of x equals x squared minus 9 over x minus 3. And this is supposed to be x is not equal to 3. All right, well, if we're going to do a graph, remember what we did with rationals. You're going to factor the numerator, factor the denominator, and if I cancel the common factors, this is x plus 3. So there's no horizontal asymptote, there's no vertical asymptote, but there is a hole in the graph. there is a hole that happens at x is 3 because you take the canceled factor equal to 0. And then if I plug it into the reduced answer, it's 3 comma 6. Now this is a line, okay, y equals x plus 3. That's a line. So if I plug in 0, I get 3. And if I plugged in negative 3, I would get 0. So watch what I'm going to do here. I'm going to go to 3 comma 6 and I'm going to graph a hole. I'm going to do 0, 3 and negative 3, 0. This is a line, so you really only need a minimum of 2 points for a line. So now watch this, okay? This is the cool part. If I want to determine the limit graphically, I need to make 2 observations before I can say the limit. Let me say that again. I need to make 2 observations, and they're right up here, okay? I need to look at the left-hand and right-hand limits. If they're the same, then I can make a conclusion about the limit. So watch this. I'm going to say the limit as x approaches 3 from the left of this x squared minus 9 over x minus 3. Okay, now watch this. If I'm coming in from the left, okay, I'm coming in from the left, I want to know what is the intended height of the function as I get closer and closer to 3 without touching it. So that's like 2.9, 2.99, 2.999999999. And look, the intended height is 6. All right, then let's look at the right-hand limit. So I have the limit as x approaches 3 from the right of x squared minus 9 over x minus 3. And if I'm coming in from the right, let me change colors. So if I'm coming in this way, what is that intended height? Hey, that's also 6. Now, I don't know if you've ever seen this before, but in math, if you do, it's like a triangle of 3 dots. That means therefore. So you do have to write this down, okay? You've got to write the 2 parts and then the final limit, okay? Because I won't know that you know. I do need you to write down left hand, right hand limits. Therefore, you can make a conclusion. So as long as the left hand and right hand limits are the same, then the limit as x approaches 3 of x squared minus 9 over x minus 3, it exists and it's 6. Okay, but notice that there was a hole in the graph. So a limit can exist even though it's undefined at that position. All right, example 3. We're going to do another one because not all graphs are rational. So this is f of x equals 3 to the x minus 1 over x. And this is supposed to say where x is not equal to 0. All right, this is looking a little exponential. So let me plug in. If I plugged in 1, 3 to the 1 is 3. 3 minus 1 is 2. 2 over 1 is 2. Let's do 2. Okay, if I do 2, that's 9 minus 1 is 8. 8 over 2 is 4. Let's kind of go on the other side and see what happens. If you get 3 to the negative 1 minus 1 over negative 1, that's 1/3 minus 1 over negative 1. Negative 2/3 over negative 1, that's still positive 2/3. So I'm not quite ready to graph this, but if you, I'm interested in what's happening at 0. So on this one, I feel like I need a little bit more information. Like I can't tell. This is not a rational function. So something is happening at 0. So watch what we're going to do, okay? Because we don't know exactly what it is. So let's do 0.1, 0.01, 0.001. Then go ahead and go on the other side. And I'm going to write over my stuff. Okay, go ahead and pause the video and try and fill in the table, because this is just an unusual graph. I don't know what's going on. All right, so hopefully you used your graphing calculator and you have 1.161. I had 1.105, 1.0992. Okay, let's see what happens on the other side. I had 0.0404, and I had 1.0926 and 1.098. So watch this, and notice I haven't done the graph yet, because this is going to help me if I consider the limits. So if I look at the left side, if I'm getting closer and closer to 0, doesn't this look like it's getting to 1.1, 1.098? It's getting closer and closer to 1.1. And if I come in from the right side of 3 to the x minus 1 over x, that's also getting closer and closer to 1.1. Therefore, my limit as x approaches 0 of 3 to the x minus 1 over x is 1.1. So I'm kind of going to do this graphically and numerically. So watch this. That's actually my whole, isn't it? Because at 0, it's not defined, okay? Because you cannot divide by 0 here. So watch what I'm going to do. I'm going to plot 1, 2. Here's 2, 4, but at 0, I have a whole at 1.1. At -1, it was 2/3. And if you have a graphing calculator, you could pop that on there, because it does look like I have a horizontal asymptote there. So kind of your big idea here with limits is you should be able to find limits both numerically and graphically. Now, something I want to point out, okay, because this happened on our Chapter 1 test, okay? On your IB exam in May, you will be asked to do both. So I know that some of you will have one method you prefer over the other. Some of you will love to just pop it on the calculator. Some of you will prefer a table. Okay, I understand that, but you have to be able to do both. So if you are given on the next quiz, find a limit numerically and you do it graphically, you will not earn full points. Okay, so I need some of you to sort of make sure you're understanding what I am asking. All right, limits at infinity. We actually already did this, so this is kind of nice. It's a quick refresher here. It says the concept of limits helps us to understand the behavior of functions for extreme values of x. In Chapter 4, you studied rational functions. This was where x was not equal to 0. So the definition for a horizontal asymptote, okay, this is not new. We already reviewed this in Chapter 4. The horizontal asymptote is a horizontal line y equals k that tells you the behavior of the function for very large values of x, i.e., what is the intended height or y value as x approaches infinity or x approaches negative infinity. I want to repeat that a graph can cross a horizontal asymptote in the center near the origin, but it will not cross it as you go far to the left or far to the right. Okay, so a horizontal asymptote can get crossed in the middle of a graph. However, a vertical asymptote does not ever get crossed, okay? So I want to make that distinction. So a vertical asymptote is a vertical line, x equals a number, and describes the behavior of f of x as x gets infinitesimally closer to the value of c, which is not in the domain of f of x, okay? So as x approaches c from the left and x approaches c from the right, the value of the function is going to increase without bound, and it either goes to infinity or negative infinity. So let's look at example 4. It says, consider the function f of x equals 2x over x minus 1. And this is where x does not equal 1. So it says sketch the function. So I can tell right away that my domain is x is not going to equal 1, and we would say x is an element of the set of real numbers such that x does not equal 1. I have a vertical asymptote of x equals 1, and I have a horizontal asymptote of y equals 2. All right, this is from chapter 4, so from the end of chapter 4 forward, it is assumed you are solid with this. We're going to make a table. The rule for me is you do 3 values to the right of the vertical asymptote and 3 values to the left. So since the vertical asymptote is x equals 1, I'm going to do 2, 3, 4. Then on the other side of x is 1, I'm going to go 0, negative 1, negative 2. Go ahead and pause the video and get your table. All right, I'm going to go ahead and blow it up a little so I can draw it better. Okay, so I have a vertical asymptote at x is 1. I have a horizontal asymptote of y equals 2. Okay, then I have 2 comma 4, 3 comma 3, 4 comma 8 thirds. Remember, this is a rational function and we want it to hug our asymptote. So I have 0, 0, negative 1, 1, negative 2, 4 thirds. Notice that the x and y intercept is the same. It's at 0, 0. So I have my equations of my asymptotes, and then let's go ahead and write down the limits, okay? So I have the limit as x approaches 1 from the left. And you can either write f of x or you can put the function in, 2x over x minus 1. And I've done like 2 one way and 2 the other. So as I come in from the left side, that's shooting down to negative infinity. The limit as x approaches 1 from the right would be positive infinity. Now we would say that the limit as x approaches 1 does not exist. Okay, so watch this. We would say the limit as x approaches 1 of f of x, we use capital D and E, and that stands for does not exist, because they have to go to the same place in order for it to exist. So those do not go to the same place. The other limits I could talk about is the limit as x approaches negative infinity of f of x. So as I travel to the left, this is approaching the horizontal asymptote of y equals 2. And remember, a limit is the intended height. In other words, the y value as x is going to that value. So now if I go out to the far right, the limit as x approaches infinity of f of x equals 2. Now, do you understand with what I have in blue, I don't have a therefore here because x wasn't going to a number. It wasn't going from the left and right hand side of one number. So this is really referred to as end behavior. And if you were in pre-calc or honors algebra 2, you are familiar with that. All right, that wraps it up.